everyone, our topic for today is about Green's theorem. So at the end of this lesson, you should be able to, number one, use the Green's theorem to evaluate a line integral. And then number two, use the alternative forms of Green's theorem. So in this section, we will study the Green's theorem. So this is named after the English mathematician George Green from 1793 to 1841. So this theorem states that the value of a double integral over a simply connected plane region R is determined by the value of a line integral around the boundary of R. A curve C given by the vector valued function r of t equals x of ti plus y of tj, where t is greater than or equal to a but less than or equal to b, is simple when it does not cross itself. That is, r of c is not equal to r of t for all c and d in the open interval. Okay, what is simply connected? By definition, a connected plane region R is simply connected when every simple closed curve in R encloses only points that are in R. As you can see in this figure 15.26, R1 is an example of simply connected plane region because it encloses all points that are in R1. So informally, a simply connected region cannot consist of separate parts or wholes. So these two figures below are examples of not simply connected plane region or closed curve, because because R2 consists of two wholes and R3 consists of separate parts. Green's theorem. According to this theorem, so let R be a simply connected region with a piecewise smooth boundary C oriented counterclockwise, that is C traverse 1, so that the region R always lies to the left. If M and N have continuous first partial derivatives in an open region containing R, then the integral of m dx plus n dy over boundary C is equal to the double integral of the partial derivative of n with respect to x minus the partial derivative of m with respect to y times the change in the area over region R. Okay, so as an example, let us use the Green's theorem to evaluate the line integral y cubed dx plus x cubed plus 3xy squared dy, where c here is the path from 0, 0 to 1, 1 along the graph of y equals x cubed, and from 1, 1 to 0, 0 along this curve y is equal to x. Okay, so from the line integral y cubed dx plus x cubed plus 3xy squared dy, we have to identify the value of m and the value of n. So from this given line integral, your m is equal to y cubed, your n is x cubed plus 3xy squared. So it follows that the partial derivative of n with respect to x is equal to 3x squared plus 3y squared. And then the partial derivative of m with respect to y is 3y squared. Then applying the Green's theorem, so this line integral can be written as the double integral of the partial derivative of n with respect to x minus the partial derivative of m with respect to y times the change in the area. Okay, the change in the area can be written as dy dx, where y is where the limits of y and x should be taken from this region, because this is bounded above by y equals x and below by y equals x cubed. So the lower y limits is y equals x cubed, and the upper y limits is y equals x. And then for x limits, it starts from this point 0, 0 to 1, 1. So the x limits is, or the lower limit of x is 0, the upper limit of x is 1. And then but recall that the partial derivative of n with respect to x from here is 3x squared plus 3y squared minus the partial derivative of m with respect to y is 3y squared. Combining like terms, so 3y squared minus 3y squared is 0. So we have 3x squared dy dx evaluated from x cubed to x and then x from 0 to 1. And then integrating this 3x squared with respect to y. So we have 3x squared y evaluated from x cubed to x. So we replace all the y variable by the upper minus the lower limit. So we factor this out, 3x squared, and then we substitute the upper limit for y variable. So this should be x minus x cubed times dx. And then simplifying further, so you have 3x squared times x is 3x cubed minus 3x squared times x cubed is 3x to the fifth, all with dx coefficient. And then integrating this with respect to x, so this 3x cubed dx becomes 3x to the fourth over 4 minus the integral of 3x to the fifth dx is 3x to the 6 over 6 evaluated from 0 to 1. Okay, so simplifying further, 3 and 6 are both divisible by 3. So this can be written as x to the 6 over 2 evaluated from 0 to 1. So if x is equal to 1, then we have 3 over 4 minus, this is 1 half. And 3 over 4 minus 1 half, recall that 1 half can be written as 2 over 4. So 3 over 4 minus 2 over 4 is 1 over 4. Okay, so therefore the line integral of y cubed dx plus x cubed plus 3x y squared dy is equal to 1/4. In example number 1, Green's theorem was used to evaluate line integrals as double integrals. You can also use the theorem to evaluate double integrals as line integrals. So one useful application occurs when the partial derivative of n with respect to x minus the partial derivative of m with respect to y is equal to 1. So therefore the integral of m dx plus n dy over curve C is equal to the double integral of the partial derivative of n with respect to x minus the partial derivative of m with respect to y times the change in the area over region R. And because this partial derivative of n with respect to x minus the partial derivative of m with respect to y is equal to 1, so this can be written as the double integral of 1 times the change in the area over this region R is the same as the area of region R. Among the many choices for m and n satisfying the stated condition, the choice of m equals negative y over 2 and n equals x over 2 produces the following line integral for the area of region R. So according to this theorem, which is called the line integral for area, that if R is a plane region bounded by a piecewise smooth, simple, closed curve C oriented counterclockwise, then the area of R is given by A is equal to 1/2 times the integral of x dy minus y dx over this boundary curve C. So as an example, so use the line integral to find the area of the ellipse with this equation, x squared over a squared plus y squared over b squared equals 1. Okay, so using this figure on the right side, you can induce a counterclockwise orientation to the elliptical path by letting the x-coordinate as a cosine theta and the y-coordinate as b sine t, where t is greater than or equal to 0 but less than or equal to 2 pi. Okay, and then using the line integral for the area, where a is equal to 1/2 times the integral of x dy minus y dx over this boundary curve C, using this equation for the x and the y coordinate, now we can rewrite this in terms of t variable. So we have 1/2 times the integral of x dy, where x is a cosine t, and then dy is the derivative of y equals b sine t, which is equal to, this is dy. Okay, so this is dy equals b cosine t. Okay, so by substitution, we can replace dy here by b cosine t and then dt. Okay, and then minus y, where y is b sine t, times the derivative of x. But the derivative of x is negative a sine t dt. Okay, so we replace dx here by negative a sine t dt. And then by simplifying further, we multiply a cosine t by b cosine t. So we have ab cosine squared t dt minus negative times negative. So we have positive. B times a is ab, sine times sine is sine squared t dt. And then factoring out AB and dt, so we get cosine squared t plus sine squared t. Then we factor this out, we multiply to 1/2. So we have AB over 2 times cosine squared t plus sine squared t dt, where t is from 0 to 2 pi. And then recall from trigonometric identity that sine squared t plus cosine squared t is equal to 1 times dt. So we have dt times this coefficient, which is ab over 2, and the integral is from 0 to 2 pi. Okay, integrating dt, we have t evaluated from 0 to 2 pi times ab over 2. Okay, by substitution, substitute the upper minus the lower, so we have ab over 2 times 2 pi. Okay, then 2 pi over 2 is pi times AB is pi AB. So that's the area of an ellipse.